Okay, so let's start. Welcome. Today, as I said, it's going to be a bit of an unusual lecture. So we're not starting from the core building information modeling topics, but we'll set the foundations of the IT skills that I think a building information modeling person should be familiar with. And that covers, well, that starts from the very foundations of IT. So it might be tricky. If I go to the right computer to switch slide. So what we consider to be information systems is the sum of all these factors. It is infrastructure, data, processing algorithms, and people. This is what we consider to be information systems. So if you make any changes to any of these, there will be repercussions to the others. All right? Infrastructure is crucial because through that you actually achieve the data exchange that you're interested in. Well, data itself is crucial because if you don't have the data, you cannot say you have an information system. Now, the procedures that you apply on those data are function of the data, and depending on them, the data must be structured in some other ways, in some different ways. With other people, of course, there is nothing of this. So any changes to any of these factors is what we are interested in from a high-level perspective. Okay? Today, though, we'll start from the bottom and we'll start looking at what IT is technically, mechanically, at some level as well. So we'll take it from the distance, really, and we look at data. So we look at principles. What is data really? How do we store it? What is the underlying structure and hardware of IT systems to be able to capture that? We look at formats on top of that. We have a quick word on what databases are practically. And then we look a bit at infrastructure, particularly in terms of, well, some hardware, but very little of it. And then a bit of networking. What are the networking principles that allow us to transfer information? Well, it's a few of you in the class, so we'll try to make it as interactive as possible, and the order of events might change depending on your input. So feel free to participate. Again, from a basic perspective, all of computation happens like this. You have some input level, some processing, and then you have the output. Now, this seems very trivial. It becomes very complicated as soon as you start realizing that at each of these steps, you need to have some sort of user interested in this data. And so you have the user that is dealing with an hardware level necessarily. The hardware will probably communicate to the operating system, and the operating system will communicate to the application, and vice versa. So at each moment during these input, processing, output operations, there's going to be a transferal of information through this chain and then back up, and then through this chain and then back up at each of these steps. So today we look at how this happens. And of course, sometimes you have a different situation when you don't have the user directly involved, but sometimes you have temporary storage of information on your disks, on the network or other types of services, and then some other processes kickstart. So you have a loop of information processing. Okay. Now we have seen that there is a physical layer, and we start with the very foundations now. How many of you can recognize this? In percentage? Have you ever seen anything like this before? Not even close. Okay, it looks like a train ticket of some sort, right? It's not. It's a computer disk. Okay. This is storage, as it started. Storage is the way for computers to tell a difference between a value and some other value. Okay? Whenever a computer can tell whether a value is X or Y, you are involved with storage, some sort of memorization, ability to memorize information. And this needs to happen at some hardware level. There needs to be a physical layer that takes care of this. Okay? Now, in time, this has changed immensely. And this is where it started. It all started with some physical system that was capable of telling whether at some specific position on a cardboard, like that, there was a hole or not. So you have a pin that goes through that hole and conduces electricity. If electricity goes through, then you have some value. If it doesn't, then you don't have that value. All right? So, conventionally, if you have a hole somewhere on this card, it means something. If there is no hole in such position, it means something else. Okay? Very eloquently put down here. This is not important because it's current, of course. This is not important at all nowadays. What's important for us to know about this is that whatever we do, we always have to remember that everything happens through hardware at some level. So today we'll try and understand how this hardware in some sort mandates the data requirements that we have. This is an interesting one. This is hardware for permanent storage. Okay, you punch this card, you make a hole in it in order to preserve information that you need to store for long term. So 3 weeks down the line, you can put this card back into a computer reader, and it will be able to tell what value, what information was stored in that card. Now, very frequently though, information is only valid temporarily. So it's something that you need to use temporarily for your purposes, and then you can forget. All right? We have this concept in the current hardware as well. Historically, we had the first solution that was found to preserve information temporarily but consistently was to have mercury lines. So you had lines or pipes of mercury where you will be hitting one end of the pipe, and this will make a wave, a physical wave, in the mercury liquid that will transfer across the pipe and reach the other end of the pipe a minute later, say. Okay? 1 minute later, you could go there and read whether there was a wave or there was no wave. Okay? And this will tell you, okay, 1 minute ago, you wanted to remember a 1 if there was a wave. If there was no wave, you know that 1 minute later you wanted to remember a 0. So, I'm mentioning this just because it's important to understand that 50 years ago, 1960 now, years ago, this was information technology for you. Okay? All of this big machine here, see the sign how small it is. This is an A4 sheet, okay? Contained lines of mercury that could be read. Each of them was capable of storing how many waves can stay in such a length. And that is 120 bits. We now start talking about what a bit is and what a byte is. 120 bits means that you can store 120 little pieces of data that are either true or false, 0 or 1. So, to a binary state. Okay? We've made a lot of progress since then. You all know that. We'll try and measure how big that progress was in the next coming slides. So the progress we've made is presented in this slide that is difficult to read, but you might. This is a century of evolution of computer speed. And it is presented in such a way that it is logarithmic. So the plot is logarithmic, which means that at each increment here of a constant number, you have an exponential growth of speed. So this, looking similar to a straight line, means that we have had incrementally exponential growth on computing speed over the past century. To achieve that, what happened was that we moved from physical patterns to other physical patterns. So we moved from some hardware technology to some other hardware technology, and then kept improving on it. So from the punch cards that you've seen that are early 900s to relays, so physical connectors that will be electromechanical, to tubes that will be solid state. Well, I would say they would not require mechanical movement to be able to discriminate between a value and another, to transistors that are, well, still non-mechanical, only electronic, but single function, to integrated circuits that include very many transistors in one single piece of chip. So the growth has been exponential. Now, can you get that joke?
Two.
Yes. Okay, so this number here is 2. It's 2 in binary. How many of you are fluent in binary? How easy would it be for you to transfer a decimal number into binary? If I ask you to write down, say, 15 in binary.
Give us half a number. Give us half an hour and I'll be able to do it.
Half an hour?
Yeah, just go to the computer and do it.
Oh, yeah, of course. No, it's important that we understand the principles, then we can move on. But the principles are crucial. So, the reason for computers to work on binary information is the one we just mentioned, that there is a hardware layer that manages everything. Okay, if you neglect this hardware layer, everything could be decimal or everything could be happening in other formats. But it's currently technically easier to make a hardware that will tell the difference between two states. Okay, only two states. Something is there or something is not there. There is a hole in the card or there is no hole in the card. It's much more complicated to make a system that will be able to discriminate 3 states. How can you do that? There is a hole, there is a small hole, or there is a big hole. Technically, it's more difficult to make such a machine. That's why binary numeric systems are at the foundation of information technology. Okay? Now, these comes with some limitations, and I would like to investigate them. Before we can move on, we'll have to look into what binary systems are. Just quickly. Why is this number 2? Just a bit of interaction here. Why do you think that means 2?
Classification.
Say again? True and false, yes. I mean, that's Boolean. So we say that if you only have 2 states, you can call them true or false, 1 and 0, red or green. It doesn't matter. You only know. You just know that you only have 2 states. Okay. Now with our traditional decimal system, that I should remind you only comes from the fact that we have generally 10 fingers, nothing else. There is no greater value in decimal or binary or anything else. It's just that we have 10 fingers. That's why you use decimal. You have 10 symbols to talk about numbers, to talk about quantities. You have 0, 1, 2, 3, 4, okay. Now, imagine you only had 2, 0 and 1. I'll better fetch a pen, I think. Oh, there's one here. Fetch that eraser.
This time you have to very interesting consumer products.
So you've done binary before,
Not like, you know the principle, how is theory, but not like.
What kind of hazard a guessing saying, the 1, 15, you look at that 5 times and then you just, you repeat it 7 times and then you add say 1 or something like that on there, so that's your feeling, you know, hazard a guessing to that.
You're kidding.
Profanity as well.
With a permanent marker.
Maybe you can use the paper seems to be
So,
It appears that way.
let's just take away a part of it. All right. It's a disaster today. Anyway, let's just break this down. It's easy. Okay. So we said we have this situation where we have 10 digits. So we start with a 0, and we say, well, the greater number than this, so any number that is greater than this, is the other symbol, 1. The next bigger number is another symbol chosen casually in the order, right? When we come to the greatest number, that symbol that we have, so the last symbol that we have, what we do is start adding, well, changing position of the symbol, right? So we put the first of the symbols that means something, and then we start again from 0. Make sense? Now remember that these are left empty, but it's like here there was actually a 0 that is now increased to a bigger number. This is all conventional, of course. Rather than shapes like 0, 1, 2, I could have shapes like a symbol like that, or a symbol like this, and a symbol like that. It's all arbitrary, right? As long as we agree that this means 1, this means 0, this means 2, we can go on. Yes?
To answer your question before with the 15, is that just 1, 0, 1, 0, like that continuously? Until you get 15?
Nope. We'll cover it in a second. So, let's assume you want to do the same thing with only 2 symbols. Same logic. The one that you apply every day without even knowing, okay? Or having forgotten, I suppose. So you start with the same thing. You have a symbol that says nothing, and you say, okay, nothing. What's the next one? We can use zeros and ones.
So it's 1.
Okay, so we go 0, 0, 0, 1. All right? What's the next one?
Then 0, 1,
1, 0. Yes. So we did the same. When we finished the symbols, we increased the next one down the line. So 0 becomes 1, 9 becomes 0. 0 becomes 1, 1, which is the last one, becomes 0. The next one down the line is, make sense? The next one is
130.
all right. You can go on forever with just two symbols. You cover all the possible numbers you can think. What's the catch? Of switching from one system to another system. This is really subtle. The catch is, and this is largely the reason for us to be talking about this, is that the amount of space, the amount of digits that you need to store a number such as 10, or actually up to 99, with a decimal system are just 2. Okay, with just 2 digits, you can store 100 values from 0 to 99. With 2 digits from a binary system, you can only store 4 different values. You have completed, you have exhausted the combinations of 2 symbols in 4 values. Is that easy to understand at this stage? Ooh, I went too fast. So we have a few numbers here in decimal, and we have a few numbers here in binary. They look just as big, but this number here actually it's made of 8 digits and can store up to 255 from 0. Whereas this number here is made of less digits, it's only 7, but can store up to millions. Okay, so there is a catch in using less symbols, in the sense that it requires more digits. The important thing, the interesting factor of this is that when we say digits, what we really mean is hardware storage elements, because each of those digits requires a physical layer for us to manage in a computer. There needs to be some sort of place physically where a computer can discriminate from one digit to another. Make sense?
Sorry. Yes,
Let's
it does
try-
make sense.
Let's try to go back a second. This card here, okay? We have a finite number of punches that we can punch through this card, a finite number of holes, right? So each of them we can consider to be a bit. So a bit being a single binary digit. So if we can, on this first line, okay, suppose we have the first line, we can drill as much as 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 holes. We know that the largest number we can possibly store in there is a 10-digit binary number. Okay? So we are finding the limitations of our infrastructure here. Very easy. We count the available spaces, and we know how big a number we can store. Okay? Make sense? We slowly progress from here now. I think we'll come back to this idea later. So, going back to this, how big a number can we store in 10-digit binary numbers? if you express it in decimal, of course, because if you express it in binary, it's going to be 1, 1, 1, 1, 1, 1, 1, 1, 1, 3, 6, 9, 10. Right? This is the highest number that we can store into 10 bits. If you want to convert this into decimal, what does it equate to?
1 exponential.
Yes. Which is? But not 1 actually, 2.
Yeah. 2.
No, much less. This is that. You are reading this as if it was a decimal number. If this was, but it's a binary number. We can only store 1 and 2s. So let's start thinking what's the worth of each of these. So this is valid 1. This is valid 2. This is no. Because just as you don't increase 10, so it's not that this one is 10 and this one is 20. This one is 10 and this one is 10 times 10. So in a binary system, if this is 2, this is going to be 2 times 2. So 4. So the next one is going to be worth 8, right? So 16, 32, 64, 128, 256. Yes. So you are familiar with all these numbers, are you not? You have seen all these numbers whenever you have been buying anything IT related. You've been buying RAM, you've been buying disks, you've been buying anything. Now with disks, lately they've started rounding it up, so they sell you a terabyte. Right. They don't go and tell you, it's actually not really a terabyte, it's a number that is close to a terabyte. So all of these numbers make sense in binary format. And this is telling you how many bits of information, how many bits the device that you were buying was capable of storing, right? And now information technology has grown exponentially. We've seen that. So currently they tell you, well, you have 8 gigabytes of RAM. It's not really 8 gigabytes, it's 8.192. Because this is the number that you get if you go on multiplying here. You get 124, 248, 2048, 8,192. So when you buy something that is 8 terabytes, it's actually 8,192 terabytes. But they round it up, okay? So we have now understood how it is that we can store numbers into decimal formats for a computer to be able to process. Okay? That's just the beginning of it. The interesting bits come later. Well, I should point to I won't cover a lot of this, but you must understand that there is always a hardware layer that deals with the things that we deal with. All right. If you want to know more about that, there is this URL here that you can go to. You'll be given this slide, so there is no need to take note of this URL. But you can learn more about binary numbers there. Now, the next step is for us to understand that computers are generally not used just for storing information. They're used for editing, working on information, making their own algorithmic decisions on information. And again, it's all based on binary, because that's all you get into a computer. You only get binary information. So it's all based on functions that can execute on binary numbers. We'll cover this very quickly, but I just want you to understand the foundations. Let's say that a computer must make a decision on something. So, I want to have an umbrella to go out today if it is snowing or if it is raining. Otherwise, I won't take that umbrella with me. So a computer can make this decision adopting one of these core. Oh no, come on. Ah. One of these core functions. So we have somewhere the storage of information. We have information that we call is snowing, and another one that we call is raining. All right? And we have a space in our hardware somewhere where there is a value that is either 0 or 1. 1 means that it is snowing. 1 means that it is raining. If it is not, now if it is snowing and raining contemporary, we have an 11 there. Might be a weird scenario, maybe it will never happen, but we have an hardware layer that is capable of storing this information. If we have a number like this, 10, it means that today it is snowing and it is not raining. If we have a number like this, 0, it means that it is raining but it's not snowing. If we have a 0, it means that it's neither snowing nor raining. Alright? So we've started storing information that is encoded in numbers, but it's not numbers. This 0 does not mean 0. It only means something else. So we are using a convention there to encode at the hardware level some information about the real world that we care about. Okay? Now, if we want to have some other value that is tell us, do we need an umbrella? We can either have some other hardware that where we store that information ourselves, 1 for we do, 0 for we don't, or we use a computational function to achieve that. So we make that decision on the grounds of this information that we already have. Okay? And it's easy for us to convert from this to that if we know our Boolean logic. The Boolean logic, or better, the Boolean operator that will help us make this decision is an OR. If you go and check OR, you can get the values of OR as a function of the input. So you have an input that is snowing, you have an input that is raining, and you have an output that is our do we need an umbrella question. And the OR function gives us what we want as an input from that. So we have 0, 0. Do we need an umbrella? 0 means not. Can you tell that these are the input values? So X being it is raining, Y being it is snowing, okay? And the output is do we need an umbrella? So not raining, not snowing, do we need an umbrella? No. Not raining, it is snowing, do we need an umbrella? Yes. It is snowing, but it's not raining, do we need an umbrella? Yes. It is both raining and snowing, some sort of horrible weather is up there. Do we need an umbrella? Yes. Okay, so we have selected a function that transforms our input into a useful output without needing any storage, but taking into account the existence of basic binary functions. And we've selected one for our purposes. Now, it's not a random function that I picked. If I had picked an AND, I would be in trouble, because AND tells you that you need an umbrella only when it's actually raining and snowing contemporarily, which is not useful for us. We want an umbrella when it is either, well, it is raining or snowing or both. Okay? So this is the finite list of options. These are all existing functions of two numbers in a binary environment. Okay? By combining all of these together, you can create an algorithm that is much more complex. After having run this test, you can run another test, so it is raining and snowing and something else, so I need an umbrella, and but wait a second, I also have a car, so I don't need an umbrella, because the car comes out and they come and pick me up and they drop me in a safe and dry place, so I don't need an umbrella. You can start building up with these basic components and the information that you have, and make arbitrarily complex algorithms. Okay? An algorithm is just a set of procedures that you use, that you execute on your data through your functions to get to an interesting and useful result for you. Okay? Tell me when you need a coffee. We have it, fortunately. So, when it comes to making up a computer that is capable of doing some of this stuff for us, historically, people will make up a physical circuit just for that. So they will actually physically bring a circuit together that will have an input from a rain sensor, an input from a snow sensor, have an AND or an OR logic in, and then use that value as, you know, to light up a lamp of some sort that will tell you, as you are going out, you need an umbrella, to make a simple example. Now, this was actually built physically, okay? Physically. And it was custom made, and it could only do that, right? Now, the next step in the evolution of computers is to try to create a generic purpose computer. A computer that where you could change the software, you could change the sequence of operation that the computer would execute depending on your needs, right? We give this for granted today. You open your computer and you install a new application. You open your iPhone and you download something from the App Store. You are changing the ways in which your computer behaves by changing the software, not by changing the hardware. But historically, you would actually physically weld together components that would do that for you. All right?
I've done it.
Say again?
I've done that.
You've done that?
Yeah, GCSE. Like in high school.
Ooh.
Did systems and controls, so that was part of it.
Yes, interesting. And you didn't know of binary? You forgot the
No,
name?
well, yeah, it was a hell of a long time ago. Jose said he's done binary before. So.
That's the trouble with the UK education system. They give you lots of things and then you forget them. Okay.
Got to think I wasn't it.
Right. So, when it comes to defining a generic purpose computer or building a generic purpose computer, I won't go into many details about that. But if you will ever be interested in that, there is a link here, www.nand2tetris.org. That's a brilliant website. It's a free course with lots of resources that you can take to understand how you can, starting from a chip that is capable of doing this function here, the NAND, to a full-blown, completely functioning computer. So all the steps to build a computer from one single logic chip. Amazing stuff, if you're interested. So, but generally, historically, the decision to how you actually build up a physical computer that is capable of resolving variable tasks and tasks that you can program at will without changing its hardware was made through basically, well, by trying to make it fast as possible. So speed was, in the past 3 decades, the most current, the most important factor for people designing computer architectures. And of course, the ability to encode and decode information and how big numbers these computers should be able to deal with. So what was the sort of problems that they could solve? This has led to the creation of a stack of hardware that would provide functionalities to the core computing engine of your PC, if we are considering a PC. You've all heard this term, CPU, okay? I think. Yes? You're very young, but you still should have heard of that. So what's the CPU for you? What do you think a CPU is? What does it mean?
The inputs will be processed.
Yes, exactly. It's where the algorithms happen. Okay, it's the core that is capable of doing the OR for the doing it properly. Okay. Now, come on. All of this technology and the failing whiteboard. There you go. All right, so we have this CPU. What is the problem with that? Is that current computers need to be able to evaluate these functions very quickly. It was possible for us to make CPUs that could process all continuously faster and faster and faster. We are now talking about gigahertz. You have heard of this. Gigahertz means, what is a gigahertz?
26.
26?
10,
All right.
10.
No, it's 9. It's 9.
Yeah,
'Cause that's
6 is mega.
Yeah.
Okay.
Sorry.
So, I think it's like this.
Yeah, it is.
We need one more, right? So this is the number of operations per second that those computers can, that those CPUs, okay, those CPUs can execute. So for each second, they can evaluate, do I need a Brody? Millions of times. Actually, billions of times. All right? What's the problem with that? There is a big problem with that. The big problem with that is that we need to be able to tell the computer the underlying data that they need that fast. So we need to be able to tell them whatever, how many billions of times per second it is snowing, it is raining. If we can't update the status of the snow and the rain with that speed, they can't make it up on their own. They will have to, get information fresh information to elaborate. If they can't get that, they are useless. They are running in an empty loop waiting for us to provide them information to edit. All right? And that's where the big bottleneck was. We had very fast processing units that were relying traditionally on slow disks. Disks could not update this information so frequently, so RAM came in. RAM is an intermediate status where we can store information that the CPU can access faster than the disks. It comes with pros and cons. It's much more expensive than the disks. Disks traditionally costed X, RAM would cost 10 times that much or 100 times that much. So you had smaller RAM than the disks, and you still have that. Your disks are terabytes, your memories are megabytes or gigabytes, right? So the whole structure of a computer is not mandated by gods, all right? The whole structure of a computer is an equilibrium of speed, played around speed. So you set up a way for the CPU to be able to get fresh information at low cost, at reasonable costs. So you would have a small amount of RAM that you can access fast and bigger spaces for storing all the information on the disks. And at some point people realized that that was not even enough. So they put memory inside the CPU, the cache. Have you heard that term? CPU cache, so its memory inside the CPU could actually be read at every instruction. RAM could be read every 3 or 4 instructions, say. And disk could be read every 1,000 instructions. So you'd have to cleverly move information around from the CPU to the RAM to the disk, depending on the purposes. I want something to be stored permanently because I need it tomorrow and in 10 weeks' time, I'll store it in the disk. If there is some information that I only need to work on temporarily and then I can discard, because once I'm out I've taken my umbrella up, I can forget whether I need an umbrella or not. That's RAM. That's something you can disregard afterwards. So all of this is, so the structure of computer as we know it is only a function of trying to make it fast. It doesn't mean anything else. It's not mandated. All right? With the current physical technology. So the solution that we came up with was to have a number of buses that would talk into a bridge, that would talk into a standardized structure that would be connected to the CPU, and it could have access to AGP bus and the RAM and so on. So the farther you get from the CPU, the slower you are. So we can see that the fastest elements are generally the memory bus that is connects you to the RAM and the AGP bus that connects you to AGP. Have you heard of that? It's the type of bus that you buy or that you use for your graphics card. Have you heard of that now? Rings a bell? Maybe. Anyway.
In the echelons of my brain, probably. Yeah.
It changes in time. It might be that it's now an old information. It's not important. What we need to understand is that all of these standards to connect elements together are designed to play with different speeds. So this is the physical hardware of a computer. You have the motherboard that contains all of these buses, and you start plugging elements into it as you need. So in this case we have 2 disks here two CPUs here. Ooh, that's interesting. We are having two CPUs now in computers. We come to that at some point. They are capable of talking to each other, of course. And we have RAM banks here. We have some power supply. We have extension buses here and there. Have you ever played with a computer? Have you ever opened one? You have.
Raspberry Pis. I saw it on your desktop before. A little small computer. That's probably the best one to get introduced to playing around with computers.
The small one, what?
Yeah, the Raspberry Pi. Or something.
Oh yeah, I have it here.
Yeah. It's a tiny little computer, a portable computer. Yeah, it's actually it works on a software system. It's good to play around with.
Well, I have it here if you want.
There's no external shell.
This is the Raspberry Pi. The Raspberry Pi, and I'll show it maybe later, it's a full functioning computer that has connection for a monitor, connection for a network card, connection for the audio device, two USB connectors, and this is its disk. It's a memory disk, but still a disk. Comes with 512 megabytes of RAM, and it runs Linux. So we'll come and talk about it later. So what was the same functions that you see in this hardware, you find in this device. What do you think is the difference?
Speed.
The CPU.
Yes.
Supply and demand.
This one has two very fast CPUs, two very large disks, very fast disks probably. Probably a lot of RAM there, maybe gigabytes of RAM. And this one has megabytes of RAM, slower clock, so the speed of the CPU is tinier. It's some speed, but you can now miniaturize things quite dramatically. This one is a full functioning computer, and it probably costed me 40 quid. Now, only for the disk, 20 years ago, I paid the same capacity disk, okay? Same capacity disk, probably much slower than this. 1992, I paid £3,000, the equivalent of £3,000. And it was this big, and it was 3 kilos of stuff, and it broke down in 6 months. So, huge progress. But you know that already. But when I think to that, it happened in my lifetime, and I'm not that old. I am getting older, but I'm not that old. So, you have, the only thing I really want to make a point about here is that you have custom hardware to cope with the speed that you need to do stuff. This is a graphic card. It's a gaming graphic card. It's capable of memorizing lots of triangles that you can show in 3D on your screen. It has ability to connect to multiple monitors and such and so on. And it has, this is an interesting part, it has a vent there, it's a fan there to keep it cold. Because all of this happens through electricity. So every time you have an impulse of electricity, the heat comes up. Okay. You all happy with that? So we now can write, and we make a small exercise, the number 33 in binary. Take 5 minutes to do that.